How did the universe start? How old is it? Why are we here? Scientists have been working to find the answers to these questions. Here's an important fellow. I'm sure you know who he is. And this guy, Georges Lemaitre, who used Einstein's calculations and theories to develop the current model for the construction of the universe, as far as they can tell. It all started with this. Actually, there was no light at this earliest point of the universe, so this is a fairly accurate drawing of the period. The entire universe was smaller than the electrons of an atom. It was almost infinitely dense, for the material of all the galaxies was in an object billions of times denser than a black hole. The entire universe was so small that it could pass through your hand without making a mark. At the same time, it had a gravitational force capable of reducing you to nothing. Scientists cannot explain how the universe was created or what existed before it. It may always remain a mystery. However, we can tell when it exploded. 13.8 billion years ago, the most powerful explosion ever occurred. This image demonstrates the earliest periods of the universe. The Gut era is when the forces of the Big Bang started moving. It took until the electroweak era at 10 to the negative 35th second after the bang for the forces of gravity, electromagnetism, strong nuclear and weak nuclear forces to separate from each other and release a tremendous amount of energy. This release of energy inflated the universe to at least 10 to the power 50 times its original size. If you want the word for that, 100 quintillion times its original size. While this is an impressive number, and perhaps the first time you heard it, this meant that the universe had expanded to the size of a grape. Remember, the universe was only the size of an electron originally, and it took only 10 to the negative 30 seconds to get to this size. It continued to expand at a furious rate, though, and continues to this day. 10 to the negative 4th second after the big moment, the universe was filled with photons. In the first 4 seconds, they formed the building blocks of the atom. These formed over the first 30 minutes into approximately 25% helium nuclei and 75% hydrogen nuclei. Interestingly, though, the universe was opaque until it was about 500,000 years old. It took it that long to cool off enough for the hydrogen and helium nuclei to capture electrons and allow photons to move freely throughout space. It really didn't matter, though, because life had still not developed. Extremely intelligent life eventually evolved, and some specimens of this species noticed that the universe acted in predictable ways. Sir Isaac Newton, pictured here, formed the 3 laws of motion. Simply stated, Newton first discovered that objects keep doing whatever they're doing until an outside force acts upon them. The Earth keeps going around the Sun because that's what it was doing when it formed out of stardust. The universe is expanding because that's what it's been doing for a while. Newton's second law of motion states that the force required to accelerate a massive object is equal to the mass of the object times the rate of acceleration. If a car weighs twice as much as another car, it takes twice as much force to accelerate it at the same rate as the first car. Newton's third law of motion states that for every action there is an equal and opposite reaction. When this person jumps off this boat, they'll propel the boat backwards with the same force. We can calculate that if the boat weighs half as much as the person, the boat will go backwards twice as quickly as the man goes forwards, ignoring water resistance, that is. However, if the boat weighs twice what the person does, it will only travel half the distance as the man does. When the person lands in the water, they are bound to be introduced to temperature. Temperature is a measurement to the average kinetic energy of the molecules of a substance. The faster the molecules of a substance move, the larger spaces between the molecules. This is what causes hotter substances to become less dense. At some point, the molecules of a substance are moving around too much for the substance to remain in a structured formation. At this point, the molecules break apart and fill whatever container constricts its movement. Liquid will maintain a fixed volume, but not a fixed shape. With water, the point that it melts at is 0 degrees Celsius. If the temperature continues to rise, the liquid will become a gas. The molecules will escape their connections to each other and assume the dimensions of whatever container restricts them. The gas will assume neither any shape nor any volume. While there is no known maximum temperature, there is a theoretical temperature 0. Scientists have developed a method to superfreeze certain substances using lasers, allowing us to reach temperatures of just thousandths of a Kelvin. Lasers, as a form of light, travels as a transverse wave. This means that the wave moves particles perpendicular to the velocity of the wave. Sound operates as both a transverse and longitudinal wave. As a longitudinal wave, it moves particles parallel to the velocity of the wave. A fascinating property of waves is their property of shifting when emitted from a moving object. This is known as the Doppler effect, and can be experienced by remaining still while a police car with its sirens blazing races past. You would notice that the siren sounds high-pitched as the car approached, but hit a lower note after it passed you. The reason for this is quite simple. Because the car is moving, it is compressing the sound waves in front of it and lengthening the waves behind it. Light follows the same concept as a wave. However, since light travels so quickly, most people don't notice this. Astronomers noticed it though. When faraway stars are traveling away from us, the light from them is tinted red, just like the siren had a lower pitch when it was driving away. Astronomers can use the redshift of stars to tell us whether they're traveling toward Earth or away from us. Light behaves in even more strange ways. Surely as a school child you noticed how a straw in your drinking glass appeared to be broken at the waterline of the glass. This is because when light waves encounter a denser substance, they slow down, if only slightly. If the light is not traveling perfectly perpendicular to the substance, they bend toward the normal, an imaginary line traveling through a substance perpendicular to the surface where the light entered the substance. Light will also bend away from the normal when moving from a denser substance into a less dense substance. However, if the light tries to leave the denser medium at a very steep angle, the light will be deflected back into the substance. This property allows us to build cables of fine transparent materials and transport light long distances. In our modern day and age, this is used to perform two important tasks. First, it allows us to bring light into hard-to-reach areas. Doctors successfully use this to illuminate internal organs for complicated surgeries and medical procedures. Internet capabilities have also been increased by the development of fiber optic cable. It allows for faster transmissions of larger quantities of data. This means that faster internet speeds are possible for lower prices. Fiber optic cable's tool, light, has been shown to have some very interesting qualities. Ever heard the term quantum? Light behaves in both quantum and wave-like pattern. This means that it can travel in a steady stream, but also in packets of energy. Quantum simply means that the energy is not on a steady spectrum, but stair-steps up or down. Walking up a set of stairs, you increase your potential gravitational energy in a quantified manner. On the nuclear level, electrons carry quantified amounts of energy. This comes from the fact that they travel in specific layers around the nucleus. Moving from one level to another either requires energy or releases energy. Many times the energy comes from a photon, the quantified type of light that acts like a packet of light. When the atom receives a photon, it raises the electron to the next electron orbit. When the electron jumps down to the next lower electron orbit, it releases a photon. Ever wonder how your microwave works? Just like light, it provides energy to atoms. Water molecules have very low rotational energy levels that are grouped together. One of the few things that can enter this type massive rotational speeds are microwaves. The discovery of this led to the creation of the first microwave oven. They excite the water molecules, which in turn transfer their heat to those atoms and molecules that surround them. Building blocks of the universe are commonly seen as just that, blocks. The table of elements is designed in such a way that it's easy to find out several important facts about the elements simply by the table of elements. At the top of each cell is the atomic number, the number of protons that are in the atom. Next comes the initials of the atom. Then the full name of the atom. A small number under its name tells the atomic weight of the average atom. This is a combination of the average number of neutrons and protons. Because it is the number of protons that are used to distinguish atoms from each other, the protons for an atom remain constant for each type of atom. Number of neutrons, however, can be quite flexible. Atoms that all have the same number of protons but different numbers of neutrons are called isotopes. Generally, however, there are about the same number of neutrons as protons. Finally, there is a number of electrons per shell. This is the number of electrons per electron level typical for this atom. If your table of elements does not list the electrons per shell, there is a simple trick to figure this out. At the top of the table, there is a number for each column, starting at 1A, and progressing to 8A. For those columns that end with A, the number that precedes the A is the number of valence electrons. The first row, hydrogen and helium, only have one electron level. The second row has 2 electron levels, the third has 3, and so on.